Okay, it's a great pleasure to welcome everybody to today's information session on Machine Learning Institute. Now, you have probably looked at the website. We will look at the website briefly. We'll look at the brochure briefly, but I'm not going to reiterate what you have already seen on the website. What I'm going to tell you is how machine learning should hopefully be able to help your careers, how it can take you forward, how it can take you, hopefully, towards the future. So without further ado, let me share with you some slides that I have prepared on this subject. Okay, so Machine Learning Institute, if you have any questions about the Institute, about the certification program, please do let me know. What I'll start with is with the definition of artificial intelligence. And that definition is due to John McCarthy. Artificial intelligence, according to John McCarthy, which was the original definition of artificial intelligence in the Dartmouth workshop that was organized by John McCarthy. It is the science and engineering of making intelligent machines, especially intelligent computer programs. It is related to the similar task of using computers to understand human intelligence, but AI does not have to conform itself to methods that are biologically observable. You may ask, what is intelligence? Intelligence, according to McCarthy as well, is the computational part of the ability to achieve goals in the world. Varying kinds of and degrees of intelligence occur in people, many animals, and some machines. So artificial intelligence has been making headlines. By the way, we are talking about machine learning, and we need to clarify people have used machine learning and artificial intelligence interchangeably. Artificial intelligence was born in the 1950s, and then it became unpopular in 1970s when it overpromised and underdelivered. And then in the 1990s and 2000s, an alternative term became very popular: machine learning. Machine learning, the focus in machine learning was a lot less on the philosophy, a lot less on the ideology of artificial intelligence. The focus was on algorithms, the nitty-gritty of how we can get the machines to do interesting, non-trivial work for us. So there was a lot less philosophizing, a lot more algorithmics in machine learning, and we keep machine learning in the title of the program. It's Machine Learning Institute. It's very much applied. However, nowadays, the terms AI, when it became popular again, and machine learning are used interchangeably. So, by the way, if you have any questions at any point, feel free to interrupt me. And feel free to unmute yourself and ask your questions if you want to ask questions. I'm actually going to ask you a question first. This painting here, what does it represent? What does it represent? Who can tell me actually in 2 words, what this painting represents? You probably cannot read the inscription on the building, but that's okay. I'm not asking for that inscription. I'm asking for what does this painting represent in terms of history. Does anybody have an answer? If you don't want to speak up, you can mention it. You can say it in the chat. Trustworthy works, industry revolution. Okay, yeah, that's exactly the industrial revolution that this painting represents. And the Industrial Revolution was, if you like, the first stage of automation. It's actually Wentworth works. So it's not clear here, given the resolution of this painting, but if you zoom in, it actually says Wentworth Works, file and steel manufacturers and exporters of iron in Sheffield. And the Industrial Revolution started around 1760 and was confined to Britain until about 1830, and included major technological changes: the use of new materials, chiefly iron and steel, the use of new energy sources, including fuels and motive power, such as coal, steam engines, electricity, and so on. It was, if you like, the first step towards automation, the introduction of machines to do what was previously restricted to humans. And perhaps the apex, I guess, the zenith of the Industrial Revolution was the great exhibition of the works of industry of all nations. Who knows what this painting shows here? Who knows where is this located? Where do you think this is located? Where exactly? What are we looking at here? What's this structure? It looks like Asia, and indeed these expos nowadays tend to take place in Asia a lot more than they do in Europe. This is London, that's right. Where in London? Where in London? And what's the name of the structure that is shown here? It is London. Let me ask you, this structure was located in a famous park in London. Which park? So which park do you think it is? And what's the name of the structure? Okay, do you guys give up? So Alex was right. Mohammed was also right in the sense that it does look quite Asian. It was, if you look at the title there, it does actually say India there, right? This pavilion was dedicated to India. Of course, there was a famous expo recently in Shanghai in 2008. But here we're looking at the expo that took place in 1850s in London, in Hyde Park. And this structure here is known as Crystal Palace. Now, if you know London, you will know that Crystal Palace is actually located not in Hyde Park, but elsewhere. That's because the structure, after the Great Exhibition of the works of industry of all nations, the structure was moved from Hyde Park to the location of the area in London known as Crystal Palace, and that's the name of this structure. It was a great exhibition. It's over 500 million people attended it in Hyde Park, and that was, if you like, the high point of the Industrial Revolution, and hundreds of thousands of objects, inventions, machines, creative works were represented during this exhibition in the Crystal Palace. So that was the first stage, if you like, of automation. Now, Who can tell me what this picture here represents? What does it represent? What historical era does it actually represent? So we're looking at the second stage of automation. So what is that second stage of automation, and when roughly did it take place? I hope I didn't confuse you with the Crystal Palace, which is not in Crystal Palace, with the Great Exhibition. By the way, this Great Exhibition is intimately connected to the history of Imperial College, of Exhibition Road, of Science Museum in London, of Natural History Museum in London. So it's linked to that Albertopolis and everything to do with it. So this is a data center, yes. So which age does this represent in history? Which age? So since we see a data center here, this is the so-called digital revolution or information age. And it started around 1950s when people thinking about computers, creating computers. And this is actually when people started thinking about machine learning and artificial intelligence in earnest. This is when 1950s, that's when artificial intelligence was born. So now we have seen these two stages of automation, the industrial revolution, the digital revolution, which started the information age. And the information age is associated with a few inventions such as the optical fibers, computers, mobile phones, the internet, World Wide Web, and so on and so forth. And nowadays, about 47% of global population have internet. Now, and that all happened since around 1950s, 1960s. So who can tell me when the third stage of automation started? What does this third stage of automation actually entail? What does it mean? What does it involve? Let me give you a quote. So this is a quote from Marvin Minsky. You've probably heard of him, right? That's from his 1969 Turing Award lecture. Computer languages of the future will be more concerned with goals and less with procedures specified by the programmer. Okay, computer languages of the future will be more concerned with goals and less with procedures specified by the programmer. And imagine how nice it would be if you could formulate a goal, and that goal, without focusing too much on the implementation detail, that goal were immediately realized for you by the machines. That would be indeed the third stage of automation, where you don't have to focus as much on the implementation, where you focus on goals. This is what I want done. And without saying how I want it done, the machine knows how to do it, right? Sounds like science fiction, but this is the historical time interval that we are now approaching. Here is a quote from Alan Turing from his 1948 paper. When a configuration is reached for which the action is undetermined, a random choice for the missing data is made, and the appropriate entry is made in the description tentatively and is applied. When a pain stimulus occurs, all tentative entries are cancelled, and when a pleasure stimulus occurs, they're all made permanent. So this idea here is the idea of reinforcement, an idea that became critical in one of the key branches of machine learning, in the branch known as reinforcement learning. And reinforcement learning was pioneered by these people, by Rich Sutton and Andrew Barter. And this is a quote from Sutton and Barter. In 1979, we came to realize that perhaps the simplest of the ideas, which had long been taken for granted, had received surprisingly little attention from a computational perspective. This was simply the idea of a learning system that wants something, that adapts its behavior in order to maximize a special signal from its environment. This was the idea of a hedonistic learning system, or as we would say now, the idea of reinforcement learning. So, we nowadays have these three branches of machine learning, which are under active development, and a lot of stuff, a lot of exciting new developments take place in all of these branches, in supervised learning, in unsupervised learning, and in reinforcement learning. So in supervised learning, you give the machine some data and say, these are the inputs, these are the outputs, these are the correct outputs. And I want you to learn how to produce these correct outputs on new data. And as you can see in finance, the outputs could be, okay, what do I want to put into my portfolio? What stocks do I want to buy, given the inputs, given the information about the market? What is it that, where does the market go in the future? Where is it supposed to move? If this is where the market is right now, okay? So these are the basic ideas of supervised learning. So you give the machine inputs, so you say, okay, these are the correct outputs. Now I'm going to give you new inputs and you give me the outputs. Right now I want you to work out of sample, not in sample. Okay, that is how supervised learning works. Unsupervised learning, you give the machine some data and say, I haven't a clue about this data. I want you to figure out what's interesting here, what's important. Perhaps there are some clusters. Perhaps there are some ways in which this data is organized and it isn't immediately obvious to me what exactly is going on. So who can give me examples of unsupervised machine learning techniques? Who can give me some examples? Do you guys know unsupervised learning? Well, I guess if you knew unsupervised learning already, if you knew all of this stuff already, you wouldn't be keen to learn. Dimensionality reduction, Alex. Yes, that's a good example. PCA, principal components analysis. You know, all of these things come under this heading of unsupervised learning, and you will be doing a lot of unsupervised learning in this course. And then finally, there is a third kind, reinforcement learning. Within reinforcement learning, you say, okay, so here is some environment. The machine is an agent working in that environment, and the environment may reward or punish the machine depending on how well the machine does in that environment, right? And the machine then learns to perform its objectives optimally in that environment, right? To maximize its reward, right? That is what reinforcement learning is about. So three different branches of machine learning, three important directions where a lot of interesting action in research, in industry, is currently taking place. And I mean, so much taking place in machine learning that I would, unfortunately, I would have to upset someone because we don't have that much time. So I can only mention a couple of results, right? I can't really mention a lot of the things that I'd like to mention, but I'll mention some of the key ideas. So, for example, there is this paper, Attention is All You Need, from 2017, which introduced transformers for the first time. And that architecture proved very, very useful in things like machine translation, where you give it one language and the machine outputs the text in another language, right? You can do that kind of thing with transformers in this particular case. So the transformer is a particular configuration of a neural network, a very important configuration. And the neural networks feature extremely, they're very important in all three branches of reinforcement of machine learning. So in particular in reinforcement learning, if you use neural networks, deep neural networks, then the field is actually known as deep reinforcement learning. And this field has received quite a lot of attention in recent years. And finance, right? But it's a hugely important area coming from healthcare and life sciences in general. There has been this huge question. How does the three-dimensional structure of a protein depend on its chemical formula? Right? This is the question of protein folding. Hugely important question. And for many years, many decades, this has been a leading question, a key question in life sciences. And this question has been solved, practically solved for all practical purposes, last year. It was a horrible year for many people, but it was a good year for machine learning. And in this abstract here, we see that what the guys from DeepMind have achieved in protein folding, right? What they called AlphaFold 2. This hasn't been published properly yet. The only thing that you can find about AlphaFold 2 is this abstract right now. But there is other stuff on AlphaFold 1 which may be interesting. So this is taking the machine, taking the chemical formula of a protein, and the protein could be a drug, could be an enzyme in the organism, nearly all important things in biology, in medicine, are proteins. So important, right? That you basically take that formula and you map it to a three-dimensional structure. That's the problem of protein folding. Now, mu0. You have probably heard of AlphaZero. And AlphaZero made headlines when it beat the world champion in Go, the game of Go. The game of Go defied many attempts at cracking it, using game theory, using computer science, and so on and so forth. And ultimately, reinforcement learning proved successful in cracking the game of Go. And now there is mu0, which is considerably more flexible than AlphaZero and previous iterations of the reinforcement learning algorithms. So massive progress has been made, and this was published in Nature. So if you are interested in reinforcement learning, I encourage you to read up on mu0. Okay, so all these things have been, so I should move this cursor because it looks like I'm taking an aim at these people, which is not what I want to do. Right, okay, let me move the cursor away. I think it's very important to really realize that machine learning is revolutionizing finance, really revolutionizing. And many careers in finance are made nowadays by people who understand machine learning and who are able to contribute through machine learning to finance. And indeed, if we look here, we have several seminal papers that have been produced on different aspects of finance using machine learning. There is this paper by Blanca Horvath, who is, by the way, in the faculty of the Machine Learning Institute. So Blanca is a faculty member, and hopefully you'll be able to learn from her. She is absolutely excellent, an outstanding researcher on machine learning, and Horvath, Muguruza, and Thomas have contributed this paper in 2020 to Quantitative Finance, Deep Learning Volatility, a Deep Neural Network Perspective on Pricing and Calibration in Rough Volatility Models. So this is using neural networks to learn very challenging, non-classical, rough volatility pricing models for derivatives, and using these neural networks to efficiently calibrate the models. So that's a big advance. That's a big advance in quantitative finance. That's that's an advance in terms of computability, what you are able to compute, but also in terms of computation speed and making these models accessible, because you effectively take a shortcut by introducing the neural network where previously you had to use much more complex mathematical machinery. Okay, so that is the deep learning volatility contribution. Another contribution by Horvath, but also by Buller, Lyons, Perez Arribas, and Wood, is this is the idea of being able to simulate markets realistically, producing indistinguishable synthetic data, very much like real market data, but synthetic, generated using machine learning methods. This is especially useful in places where data is sparse, where we don't have enough data. So this will be of interest to you if you are interested in generating data for example, for Monte Carlo simulations or for backtesting, to supplement historical data with synthetic data produced using this new approach from last year, market generators. Any questions so far? Any questions? I'm just telling you what kind of things you can do with machine learning nowadays. There are a lot of applications of reinforcement learning in finance. Here is, for example, a piece by Coleman Ritter, Modern Perspectives on Reinforcement Learning in Finance. Right. Then there is the Q-learner in the Black-Scholes-Merton worlds by Halperin. So this paper presents a discrete time option pricing model that is rooted in reinforcement learning, and more specifically in the famous Q-learning method of RL. And it creates a risk-adjusted market decision process for a discrete time version of the classical Black-Scholes-Merton model, where the option price is an optimal Q function, while the optimal hedge is a second argument of this optimal Q function, so that both the price and hedge are parts of the same formula.
Hey Paul, this is Ravi. Whenever is a good time for questions, I can.
You can ask me now.
Okay. Have you seen in your experience, using machine learning for sort of looking at trading signals? Generally, with back testing, based on technical indicators, you get this buy sell signals, right? Do you think machine learning could be used over there in that part of it?
It can, and it is used in that part of finance, and I would recommend you to look at the two books by Lopez de Prada. So I would recommend those two books on this specific subject. They're really excellent.
Sure, definitely. I think, yeah. And I think, just to follow up on that, I'm just sort of, I know the basics well, but, if the question is wrong, please forgive me, but would backtesting and machine learning be two different techniques, or you would sort of even backtest all the, ML generated data, and would you combine the techniques?
When I talk about backtesting and ML generated data, referring to these kind of techniques which are very new using market generators, right? But in general, when people backtest on historical data and the machine learning method used, for example, for predicting future prices, that's one way of doing it. Another way of doing it is to use machine learning to decide when to place the orders. So you could have the machine learning algorithm feature in different parts of this process, in prediction of prices, in the placement of orders, and we'll look at a few of these articles as well, a few new approaches to this, and without necessarily using it to generate data. You could be doing this on historical data. But there are approaches where you generate you simulate data as well. This is less common than using historical data.
Got it.
Okay, does that answer your question?
Oh yeah, definitely. I think with simulation of data, you would use something like a Monte Carlo simulation and just
Well,
sort
you
of
could use historical data. You could use historical data,
Okay.
right? The advantage of market generators is that it captures when you are fitting a Monte Carlo method, you would be fitting the first few moments, right? You wouldn't be you would be simulating you say, okay, let me look at this data. It looks to me like the Ornstein-Uhlenbeck process, okay? Let me Monte Carlo the Ornstein-Uhlenbeck process, but the real data may not be coming from an Ornstein-Uhlenbeck process, okay? It could be something very different. And so instead of doing that, you could say, okay, I don't really know which process this is. Let me try and teach the neural network to generate this process, but I don't know whether it's Ornstein-Uhlenbeck or CIR or some fancier process or something like that. So this is how you could use machine learning in Monte Carlo simulation, right? So it allows you to generate more sophisticated data than you would normally generate using simple Monte Carlo techniques, because there is always this modeling step. You say, okay, let me look at the data. I think it's an Ornstein-Uhlenbeck process, okay, which may not be true. Yeah. So this is how machine learning can help you generate more realistic data. Okay, but that's just one way of using it.
Got it. Yeah. Thank you. Yeah.
Okay, any other questions? So I'm going to review some other applications, right? Some other applications such as, okay, this is an upgrade on the previous paper that we were looking at. Fitted queue iteration, inverse reinforcement learning, and things like that. So you can find all this in our recent book with Igor and with Matthew, which is called Machine Learning in Finance, and it's available from Springer. If I'm not mistaken, correct me if I'm wrong, Ed, I believe that Chris actually sends it to all of you as a present when you sign up on Machine Learning Institute. Right, so I believe you received that book as a present. So there you can read up on all these reinforcement learning things. Okay, there are other applications of reinforcement learning to hedging and dynamic replication of options and so on. There is this work by Coleman Ritter, which is well worth reading. So it's from 2019. So I'm only talking about very recent stuff now. There is another approach to deep hedging using reinforcement learning by Bilokon, Teichmann, Wood, Mochen, and Kochums. So there is this paper here, which is also worth reading. It's also from 2019. I think these are. I think I wanted to show a few more papers. I'm wondering why I skipped. I shouldn't have skipped. Okay. Yeah. So somehow I skipped quite a lot of material. Okay, we were here. Okay, we were looking at reinforcement learning by Coleman Ritter. Then there is deep hedging by these guys. I think we've mentioned that as well. There is another paper on using machine learning for hedging derivatives by Kaur, Chen, Hull, and Poulos. Right, that is for derivative hedging, for derivative pricing, how to use reinforcement learning for that. And another paper by Dixon and Halperin on G-Learner and goal-based wealth management with reinforcement learning. So it's meant to be of interest if you are into wealth management, into pension funds, into money management, and so on. So this is the approach: how to manage your investment goals using machine learning. Then there is, if you are in the world of electronic trading, and Ravi, you mentioned that you are, right? And then there is a question, okay, so I want to execute this order. I want to buy a large number of shares of so-and-so. How do I split this order? How do I optimally execute it? And there is this paper by Ning, Lin, and Jemangal on this, again, using reinforcement learning, a particular variant of it called deep Q learning, on how to do this. Maybe of interest as well. What else? There is another interesting paper, how to do this in the cryptocurrency setting. How can I place orders optimally in the cryptocurrency, on a cryptocurrency exchange or across multiple cryptocurrency exchanges? So there is this paper by Schnaubelt, which I think may be of interest to you, and it's worth looking at as well. So a student of mine, together with Jack Jacquier, my colleague from Imperial, we are preparing a paper on this subject as well. So there is an advance using probabilistic learning as opposed to just deep reinforcement learning for optimal placement of cryptocurrency limit orders. So this may be of interest as well. This is very currently in preparation, but hopefully you will be able to see this paper soon. Okay, and I've mentioned this book. If you're interested in this, I would recommend this book that I have co-written with Matthew Dixon and Igor Halperin. So the book is called Machine Learning in Finance, From Theory to Practice. And I hope that you find this book interesting, and you will receive it when you sign up for the machine learning course. So it's hopefully, it hopefully will be of interest to you. There are quite a few references that I mentioned in this very brief talk, introducing some of the recent trends and developments in machine learning in finance and beyond finance. So here are the references that I've mentioned. I think what I would like to do now, I would like to introduce the faculty of MLI. So let me do that. Okay, so now you can hopefully see the biographies. I wanted to introduce the advisory board first, right? And these are distinguished people you have certainly heard of. Heli Edgeman, who is the Professor of Mathematical Finance at Birkbeck, University of London, as well as at Johns Hopkins, one of the founders of modern finance, and Piotr Karasinski, Director of Client Solutions at Algodynamics, an expert quant who has made some outstanding contributions to quantitative finance. And you have probably heard of the Black-Karasinski short rate model. And I'm going to introduce the faculty, Terry Benchavel, founder and principal of Benchavel Scientific, Blanca Horvath, Honorary Lecturer, Department of Mathematics, Imperial College, as well as Lecturer at King's College London. Mike Croucher, Technical Evangelist at NAG, Numerical Algorithms Group. So you have probably heard these names as well, leading quants in their area, leaders in their field. Alexey Kondratyev, Managing Director and Head of Data Analytics at Standard Chartered Bank. Francesca Lazzeri, Machine Learning Scientist at Microsoft. Harsh Prasad, Vice President at Morgan Stanley. So, again, so we have leaders in their respective fields and major contributors to machine learning research, in particular in finance. And we have Adriana Sares Kashiyama, who is a research fellow in computer science at University College London. A lot of modern machine learning is created at UCL. There are people with outstanding expertise in that area at UCL. And I would like to mention the Deputy Head of Faculty, Ivan Zhdankin, who is quantitative analyst at JP Morgan Chase. And you will be talking to Ivan a lot. He has a lot of experience, a wealth of experience in machine learning, and has made some very exciting contributions to machine learning. And finally, I'm the head of faculty. So if you have any questions for me, please do ask them, and I'll be delighted to answer them if I can. So on the same page, you will be able to find the information about the structure, the various modules. There are 6 modules. The first one is the second is unsupervised learning. The third is practitioner's approach to ML. The fourth is neural networks. The fifth is deep learning, including reinforcement learning. And module 6 is on time series. So I hope this is of interest, and I hope you have learned something new today. I'm not going to read the same material that you would otherwise find on the website, but I'm happy to answer your questions in this material, and hope that you have learned something new and useful and interesting today. Are there any questions?
Hey, this is Ravi. I think, Paul, I spoke to you earlier. I think in order to get ramped up, I'm sure there are a bunch of prerequisites, I believe, right? And from a learning standpoint, would always a bottoms-up approach be very viable? Or, like, should we just get the high-level basics? Just so that, I'm also reading a book called Introduction to Statistical Learning, that just to get a little sense of, all the machine learning algorithms. They seem to sort of emphasize on some of that stuff at a very basic level. So, yeah, maybe if you could just sort of share your thoughts on that.
Yeah, so the program includes some primers. In particular, it includes a primer on Python. There are additional resources that you can find in the MLI Online Library. You can find a maths primer as well on linear algebra, optimization, probability, and statistics. So hopefully, you will find that these will help you transition into the study of the course. So there are a couple of primers that we have designed for this. But the best advice that I can give you is actually immerse yourself in the program and learn what prerequisites you need on the go. And in this way, you'll be able to cover the precise prerequisites that you need, because otherwise you may get slightly distracted, because things like, for example, optimization theory is a huge field in and of itself, and you would probably learn it more effectively if you look at the kind of questions and problems which are relevant to the specific modules that you are taking. Right, so hopefully this may be, in your terminology, this will be a top-down approach. So maybe I would recommend that. Does that answer your question?
Oh yeah, absolutely. And I think, that I feel like, I'm slowly sort of moving towards that approach, because I've started looking into linear algebra and it's sort of very abstract.
I would advise to do both at the same time, right? So on linear algebra, for example, what I would recommend in terms of preparation, I would recommend that you look at Gilbert Strang's video lectures on linear algebra. They're really excellent, and he's a very great teacher. He's very good at explaining linear algebra. So I think that would be a good entry into this field.
Got it. So the 3 blue, 1 brown YouTube, I believe. Yeah, I do remember that. And also, I think there seems to be a KDB workshop session available in that.
I think that it's worth asking Ed whether it's part of the program or not. Maybe he can clarify this. So there are questions. Are the lectures okay? So we will check. It looks like it is part of the course, but we will check. We will double check whether it's part of the course or not. Right. I do teach KDB on the sister qualification, which is Quantitative Developer Certificate. I do teach KDB on that, and we dedicate an entire module to KDB.
Got it. Yeah, thanks.
Are there any other questions? So there is a question, are the lectures pre-recorded? Yes, the lectures are pre-recorded. What time do they occur? The lectures occur on Tuesdays, either at 6 or 6:30, I think, depending on the lecturer. And normally, when there is no coronavirus, the lectures actually take place in London, right? They are recorded live. I think that's a correction from Ed. They are recorded during the lecture, right? They do occur in London on level 39 in Canary Wharf. And you are welcome to attend them in person when there is no quarantine, right? But now that there is quarantine, they take place over WebEx. And I'm delivering the lectures from home at the moment, right? But we do hope to return to in-person lecturing when the quarantine subsides and the situation improves. How many hours per week do you think the full-time course will require from an individual? I would say that it's a good idea to spend maybe of independent study. So there is a 2-hour lecture, maybe spend another 8 hours. So I would say maybe 10 to, depending on how enthusiastic you feel, to 20 hours per week. I would say 10 would be a good start. Maybe if you are really enthusiastic, you can put in more hours, right? Does that make sense? Any other questions? Any other questions? There are quite a few of you here, so I'm wondering, there haven't been some of you who asked questions. Now is the last opportunity, because if there are no more questions, we'll be concluding the session. Now is your last chance to ask questions. Please do let me know, and all questions are good. We'll be happy to answer all your questions. So now is the time, if you have questions, to ask them. No questions? You can ask in the chat or you can ask in person. You can unmute yourself and ask the question. Okay. If there are no questions, then thank you all for attending the session, and I hope you can feel free to email me if you have any other questions, and I'll be happy to answer them. Thank you very much for coming, and I hope that you have very enjoyable careers in ML and finance, and I do hope to see you on the Machine Learning Institute course. Looking forward to welcoming you in person, hopefully, or online.